Good day everyone. So I decided to have a recording of our discussion on Laplace transformation so that you can go back to this again whenever you need to review or you needed to prepare for your exam later on. So anyway, all of this here are discussed, or 90% of the things that are written in the slides were already discussed in your advanced engineering mathematics. So dynamics and controls uses Laplace transformation as a standard notation because it simplifies the tedious process of having to use integral calculus in processing differential equation or finding the solution of differential equations. Laplace makes it easy because the original DE is converted into an algebraic operation. Now, it is also very handy and easy to use because when we do block diagram analysis later on, it's the function of S or the transfer function that appears in the blocks. So we're not integrating on the diagram, but rather what is seen on the diagram is just the representation of the transfer function of that particular system illustrated in the given block diagram. Now again, DE is used for finding solution of differential equations. It's beneficial because it makes linear control system analysis easier, and it also allows us to determine the transient response to the different types of inputs or disturbances based on the transfer function that was derived using a differential equation. And it was derived using Laplace transformation. So Laplace transformation is defined mathematically as the integral from 0 to infinity of the given function times its product with e raised to minus st. Now this particular integral was used in deriving the formulas for the Laplace transform of basic functions. So you could see in the bottom part of the slide here that your constant will have a Laplace transform of a over s, and your exponential function will have a Laplace transform of 1 over s plus b. This b is the constant that appears in the argument of your exponential function. Anyhow, these derivations are not new to you because they were already shown to you in advanced engineering mathematics. So Laplace transformation does not contain any information as to the behavior of the function when time is negative, that is when time is less than 0. And not everything or not all function of t that you can convince, that you can rather think will exist. There's no such thing as all function of t having a function of s. We know that Laplace transform is linear because we can evaluate the transform of each of the term of our function separately using the appropriate Laplace transform formula. Now, the main goal of Laplace transformation is to convert the time variable or the t variable to a variable of s. Now, here are the 9 formulas for the function of t's that we commonly encounter in controls. We have the unit step function, which is 1 over s, the exponential function, which was discussed a while ago as 1 over s plus a being the constant that appears in the argument of your exponential function, then the t, which is the ramp, which is 1 over s squared, the sine and the cosine having similar functions of s, differing only in the numerator. This unit impulse function has a Laplace transform of 1. The Laplace transform of a polynomial raised to n, where n is a positive whole number, is n factorial over s raised to n plus 1. And in advanced math, we call this two as the first shifting property of Laplace, wherein a given standard function is multiplied to an exponential function. What we do, we just translate the transform of that particular function. So if originally the sign will have this, or the s in this particular formula will be converted to s plus a. Why? Because we have a minus a here as a constant that appears in the argument of your exponential expression. But in terms of the pattern or the form of the formula for the sine and the dump sine, same thing with the cosine and the dump cosine, the pattern is still the same. We only alter the s by shifting them. And as such, by shifting them, we call this one the translation of the transform. So Laplace transformation is linear. It follows that its inverse Laplace transformation should be also linear. The Laplace transform of a derivative is the primary formula we're using to evaluate a differential equation, and there is a detailed explanation later in the example. As for Laplace transform of integral, the integral has to have first limits of 0 to t. So if the given integral is not having limit 0 to t, then it's impossible for us to get its Laplace transform directly using this particular formula. So what does this formula mean is that you just get the Laplace transform of your function here that you're supposed to integrate from 0 to t and then divide it by s. That is already the Laplace transform of this integral of your function. Now for Laplace transforms of derivative that was mentioned here in property number 3, the formula is always following a pattern. If it's a second order derivative, we start with an s raised to the order of that given derivative, and it's always multiplied to the function of s. So if this function is a y, or if this function is an x, this f here, this should be a y or an x also. The next term will be a decrease in the exponent of s, so this is now s raised to 1, until we reach s raised to 0. The second term will be a multiplier, we'll have a multiplier of the function evaluated at 0. So if this function is y, so this should be y of 0. And the next to that will be the derivative of that function evaluated at 0. So now you have s times f of 0. The next would be s raised to 0, that would be 1, f prime of 0. If your derivative here is a third order derivative, you will be ending here with an f double prime of 0, because we are always ending with the order of the derivative evaluated at 0, which is less than the order of the given derivative. And this one, if this is 3, this will also be starting with s cubed, next will be s squared, next will be s, until we reach s raised to 0. So that would be the pattern to follow in determining the Laplace transforms of derivatives. And it's the primary formula we're using in processing differential equations. So Laplace transforms actually only appears on the first part of your differential equation processing to get its solution. So the ordinary differential equation provided with initial conditions will be transformed using the formula just discussed and other formulas that are also applicable. Then we convert the transformed equation or the algebraic expression into this form, wherein what is left on the left side is just the function of s of your unknown function or of your dependent variable. After that, we inspect the denominator. So if the degree of the denominator here is of order higher or is of degree higher than 2, there's a need for us to factor. We factor the denominator. That way, we can process it using the method of partial fractions. So this particular single rational expression will be processed into its equivalent partial fractions. After you have done that, you determine the coefficients of your partial fractions and take the inverse Laplace separately of all those terms. That would give you the solution of your differential equation as the last step here in the process. So we have Laplace transformation, we have algebraic manipulation, we have method of partial fractions, we have inverse Laplace transformation. That would give us the solution of your your t. Now, this is an example of the processing of a differential equation using Laplace. We use Laplace transforms of derivative here. You don't see a y of 0 already after s, y of s, because y of 0 is equal to 1. Then the next term would be a 4 y of s coming from the Laplace transform of y. Then your 2 will be a 2 over s if it is transformed. Next step will be converting our algebraic expression here into a rational expression on the right and a single unit or a single term here on the left, which is the function of s of your unknown function. We can do this. We can find the y of t for this expression using partial fractions also, method of partial fraction, and that should be giving you 0.5 plus 0.5 e raised to negative point t. This is already the solution of our differential equation. We can also have an example here wherein the left side is third order and the right side is first order. Unknown function here is y, unknown function here is u. Your dE is also provided with initial conditions. So we call this initial conditions. Now, if we would take Laplace transforms of the derivatives here and this particular term here, our answer would be this. If you notice, you don't see a y of 0 anymore, a y prime of 0, a y double prime of 0, and a first derivative of the u of 0. Why? Because anyhow, all of them have values equal to 0. Now, the u here is to be viewed as the unit step function. So, its Laplace transform is u of s. Now, if we will again manipulate our algebraic expression here to something in which the left side would be left only with the unknown function, its function of s, and the rest written on the right side, it would be this expression. Okay? Now, you don't see a u of s because u of s was already changed to 1 over s. We know for one that the unit step function has a Laplace transformation equal to 1 over s. So, it was changed already to 1 over s here. Now, if you look at our denominator, it's of degree 3, and we cannot have this inverted right away. So, we need to have this factored, and that's done here. If we factor, then our original rational expression is now converted into this equivalent 4 partial fractions. Now, we do determine the coefficients alpha 1, 2, 3, and 4 here before we find the inverse Laplace of these 4 partial fractions. So, alpha 1 is 1/3 upon using this value for s. Then, alpha 2 is 1, alpha 3 is negative 3, and alpha 4 is 5 over 3. If we substitute back these alphas to the partial fractions, it would be something like this. And you can readily have the 4 partial fractions inverted, yielding this solution for your differential equation. If you would be asked for the final value of the function or the value of the function after a very long time, the value of it will be 1/3 after you substitute infinity to all the t's that appear here in your solution for your differential equation. The factors that you are seeing here are all linear, but there are also factors we call repeated linear. We also have quadratic factors, and we have repeated quadratic factors. That would be for you to review because all of those were discussed in advanced engineering mathematics. Now, for property 5 and 6, these are very, very beneficial theorems because it will not anymore require us of going through the tedious process of inversion and then substituting the value that is appropriate for the t whenever we want its initial value or final value. So So all we have to do is deal directly with the given or provided function of s. We multiply it by s and evaluate the limit of such product. If it's the initial value of the function, we evaluate the limit as s approaches infinity. If it's the final value of the function we're after, we evaluate it as s approaches 0. The initial value theorem does not have any limitation. The only thing that you will be required to do here is for you to use L'Hopital's rule or techniques in converting an indeterminate form of your answer here to something that is acceptable. But it does not have any limitation. As for the final value theorem, there is a need for you first to check whether if you substitute real values of s greater than 0 with the product of your s times function of s expression, if the answer will not be equal to infinity. If the answer will not be equal to infinity, then the final value theorem will or can be used. If it's equal to infinity, then you have no choice. You have to invert the given function of s to get the function of t and substitute infinity to all the t's, so that you'll be able to find the value of the function as t approaches infinity, or that is what we call the final value of the function. As an example of these two properties, I have here a function of s whose denominator is 4th degree, and if we're going to apply the formula limit of s times y of s, as s approaches infinity for our initial value of the function, you will notice that we will get rid of this s here, and if we substitute infinity for all the s, the rational expression will be indeterminate because it would be an infinity over infinity. If that is the case, you are to first use techniques learned in calculus or L'Hopital's rule so that your indeterminate answer will be something that is acceptable. If you will do that, I give that to you as a review exercise, your answer for that will be a 0. As for checking whether the final value theorem is applicable here, you just substitute a value which is greater than 0 for s here, because this s is already taken out because of the multiplication of the s here. If the answer will be something that is not equal to infinity, then final value theorem is applicable. And in this sense, it is applicable because our value will be something that is not infinity. If we substitute 0 for all the s, our answer will be 1/3 for the final value of our function, or the value of the function after a very long time. Now, this final value of the function after a very long time is also referred to as the offset or the steady state error. Here, you have your y of s, you multiply it with s, so we get rid of the s here. Then we evaluate the limit as s approaches 0. The value is a. This particular example illustrates that for the steady state error, or for the offset of a function that is subjected to a unit step function of value a or of magnitude a, the value of the offset or the steady state error is simply the magnitude of the unit step function, and that is the a. That is the a. Or if you look at the transfer function, after multiplying it with the s, it is the gain here, the constant that appears in the numerator of your function of s. Now, the 7th and the 8th property are not new. They are properties also discussed in advanced math. However, they were just given a different name there. The property number 7 here is the second shifting property of Laplace, and it is being used when the t in your original function was translated. So we say the function was translated by subtracting from it a value which is a constant. This capital T is a constant. In advanced math, this is equivalent to a. So we say the function was translated because the t have been altered by subtracting to it a value which is a constant. This is in the case wherein the system, the physical system that we're talking about in controls, is experiencing dead time or time delay. So whenever this happens, then we are saying that there is a translation of the function or the time translation. This normally occurs in the transportation of fluids in pipes or whenever we take data from a sensing instrument. So all sensing instrument has some degree of lagging and there's no instantaneous measurement of anything. So as such, we say there is some dead time. Okay, that value in which we're not able to account because of that small amount of time, the lag time that was used up in sensing in the case of sensing instruments. Now, property number 8 here is the first shifting property of Laplace. This happens when your function of t is multiplied to an exponential expression whose argument is a. So what is happened is your transform this time, the Laplace transform this time, was the one that was translated. Translated in the sense that your s in the answer were all changed to s plus a being the constant that appears in the argument of the exponential function that was multiplied to your function of t. In here, we say that your function experiences what we call complex translation. As to the transform, we say that there is translation of transform. This is the first shifting property of Laplace. The last two properties here has something to do with a particular disturbance, in the case of the pulse function, and an approximation of an actual disturbance, which is the unit impulse function. A pulse function is a function which has a magnitude only on the time duration that it is occurring. Based on the definition, it will have a value of 0 for time less than 0. It also will have a value of 0 for time after the duration of such pulse or such occurrence. So it will only have a magnitude here defined as 1 over h on the time interval 0 to h. So it's a sudden but unsustained type of disturbance. I'm referring to the pulse. That is the case. All you have to do is look at the magnitude of the pulse and write it here. 1 over h is the magnitude. So in the formula for the Laplace transform of that pulse, it's the first thing that you write. The magnitude of the pulse followed by this expression in which you have an e raised to minus hs. What is this h? That's the time duration, the duration in which that particular pulse occurred. If this is 2 seconds, this must be 2. If this is a 10, for the 1 over h, this is a 10 as well. So just recall the format or the pattern of the Laplace transform of a pulse function. The unit impulse function is an approximation only of the actual pulse when the time duration is very short, when it only happened for a fraction of a second. If it only happened for a fraction of a second, then we can approximate the actual pulse by a unit impulse or by an impulse whose magnitude is equivalent to the pulse. To illustrate what I mean with the unit impulse or the impulse function being used as an approximation of the pulse, I will have this illustration to end with. Your pulse here is of magnitude 1 over h. This could be any constant. The duration of the pulse is only good until h time. This could be any constant. If this h time is so small that we shrink this part, we let h approach 0, this rectangular block here will be replicated here, or shall we say reflected here in the origin as an extending line, or as a line that is extending infinitely upwards. That is when we let h approach 0 or its value is very small, we can approximate the actual pulse by an impulse. or the Dirac delta function. If that is the case, the Laplace of that function would already be 1. So if the magnitude of the function, of the actual function rather, is 20, then the magnitude of the approximated pulse to an impulse would also be 20. So your Laplace transform would also be 20 because that would be 20 plus 1. So again, the impulse is a non-existing function. It's an approximation of the pulse whenever time duration is so short that the value that you will be getting would be very close if you treat it as a pulse or an impulse. So everything that we have discussed here, or I have discussed here, are all reviewed today. 90 or 95% of which have been discussed in advanced math. So everything we will be using in processing differential equations used to model physical systems. So we will not be integrating. Maybe sometime, for a very short time, we might be using it, but most of the time, our derivation for the transfer function will be something using Laplace transformation. So I will post this in Canvas. Just put your question on the reply box under the discussion should you have any more questions related to the topic discussed. Thank you for listening.